Alright friends, welcome back. In this video I'd like to go ahead and take a look at section 5.4 of your textbook, and as you can see according to the title, we're going to be taking a look at equations today that involve exponentials and logarithms. So let's get started with that. So now that we have talked about what exponentials and logarithms are, and we've gone ahead and talked about the properties of logarithms in the previous video, what we're going to go ahead and do is start to introduce you to equations involving exponentials and logarithms. And so if you ever have an equation involving an exponential, meaning some base number raised to an exponent that has a variable in it, then these would be the steps that you would want to go ahead and perform to solve that equation. Okay, and these basic steps here are in the same general spirit as the steps that we've used to solve various types of equations this year. Whether it was your absolute value equations or your square root equations or whatever we had, the general strategy was always to go ahead and isolate the special expression in the equation. So isolate the absolute value, isolate the square root expression, or in this case with exponential equations, isolate the exponential. So get rid of any extra 2 timeses in front, or get rid of any extra plus 5s in behind the exponential, right? So we want to get that by itself so that after that we can undo it. So that's always been the same general problem-solving strategy that we've taken for solving various types of equations, was isolate it and then undo it, or apply an inverse operation to it, in other words. Okay, and so the inverse operation, of course, to an exponential is going to be what it says here in step 2, which is to take a logarithm of each side. Okay, so once you get the exponential by itself, we're going to undo it by applying a logarithm. And then after that, we may find that we need to go ahead and apply some of those logarithm properties that we saw in the last video. So if you haven't had a chance to take a look at that, then I would highly recommend that you do that before continuing with this video. But then after that is just going to be using your inverse operations to solve for your variables. So I'd like to go ahead and demonstrate that here in example 1, where it says find the solution of the equation correct to 3 decimal places, which means that we're going to go ahead and get a decimal as our final answer here. But we have an equation like this, right? So this is an exponential equation, and remember that the goal here is that we want to first think about how we might go through and isolate this exponential right here. And so by exponential I mean this right here. So this is a base of Euler's number, so that number e that we've been talking about, raised to the power of x. We want to isolate that as best we can before we can continue with the equation here. So I'm going to get rid of that 2 times out front, and of course the way that we always get rid of multiplication is through division. So I'm going to divide both sides by 2 to start, and that's going to leave me with, on the left-hand side, the Euler's number to the power of x, and that is going to be equal to 12 divided by 2, which of course makes 6. Okay, and now that you've gotten this exponential completely isolated, it's time to undo it. Okay, so again, that's the general strategy. Isolate it and then undo it. And the way that we undo an exponential, of course, is we apply a logarithm of both sides. The question becomes, though, what logarithm, right? We have logarithms of basically all the different bases that we've taken a look at, right? Well, what we want to do is we want to go ahead and specifically focus on the base of our exponential. And of course, the base of our exponential is Euler's number here. And so that means on both sides of this equation, what we're going to need to do is apply the logarithm with a base of that same base as our exponential, or in other words, a logarithm with a base of e. And you may remember that that is our natural logarithm. So we are going to go ahead and apply a natural log to both sides of this equation. Okay, and so that's going to be the natural log of e to the x is equal to the natural log of 6. And I would like to be able to erase that. There we go. Okay, so e to the x, and that is equal to 6. And of course, what happens here? Well, because we're applying a logarithm with the same base as our exponential, we look at these as inverse operations that undo each other. And what happens here is we're just left with whatever the exponent was. And here that is just going to be the variable x. And we see here that that's just going to equal the natural log of 6. Okay, now if we were interested in just writing our answer in its exact form, then we would go ahead and box this as our result. X is the number, the natural log of 6. But if we wanted to go ahead and get a decimal approximation for this, to just kind of get a feel for what the value of that number is, then we can go ahead and reach for the calculator. Remember that your natural log button is to the left of your number 4 key down below. We're just going to go ahead and type in the natural log of 6, and it's going to give us this irrational number here. We're just going to go ahead and round this to 3 decimal places, so that's going to be 1.792 if we were to do that. So x is approximately equal to 1.792. So either representation, whether it is going to be the exact form ln of 6 or the approximate form that you see here in this decimal, that is going to be our final answer. Okay. Now remember that anytime you solve an equation, you always want to go back and make sure that you check the result just to make sure that you have the correct answer here, and remember that we can always be doing that in the calculator by using the store function, okay? And so what I'm going to do, now that I've already typed in the natural log of 6, what I'm going to do is I'm just going to immediately press the store button, and you notice what happens here is that the calculator puts ANS in there, and what that stands for is it just stands for the previous answer that you've got from the calculator. So it's going to take this decimal number, 1.791 blah blah blah, and we're going to go ahead and store that into X just as always, which you can see here that it just copies down that same number, just confirming for us that that was stored into X. And I'm just going to go ahead and type in the left-hand side of my equation that I originally had. So 2 times e to the power of X here. So 2 times e, remember that to pull up e to the power of, you just have to press second ln. And then we want e to the power of X. And because we stored that number into X, it's going to do all the operations. And keep in mind what we're looking for. We're looking for this to equal 12, the right-hand side, so we can confirm that we got the right answer. And when we press enter, we do, in fact, get 12. So that is going to be a correct answer for us. Okay? Always important that you go back and check your results to make sure that you have the right answer. I've gone ahead and shown the work here for example 2 just to save time in the video because it would be so similar to the last example there. So you can see not only did I show all the steps, but I did a quick screenshot of what it would be in the calculator just to confirm that this is our correct answer. And again, I am applying a logarithm to both sides, and the logarithm that I choose is going to be dependent on the base of the exponential that I'm trying to undo. So here, because the base is e, I'm going to apply a log with the base of e, or in other words, your natural log of both sides. But you could pause the video and just kind of work your way through that problem and see that that does check out in the calculator, that that is going to be our correct answer. Moving right along here, just to take a look at some other types of examples here. You might have an exponential equation that looks like this, where you might need to do more of a process to undo all the operations that you see to get that exponential by itself, okay? So the exponential that we do want to get by itself, of course, is this right here. So that's going to be your 5 to the x power. And we see a minus 2. We're just going to go ahead and undo that by adding 2 to both sides. It's going to give us 2 times the exponential is equal to 32. And then after that, we're going to get rid of that 2 times in front by simply dividing both sides by 2. And then we end up with this. The exponential, 5 to the x power, is equal to 32 divided by 2, which of course makes 16. Now, again, in order to think about undoing this exponential, we need to apply a logarithm of both sides with the same base as our exponential. So because the exponential has a base of 5, for that reason, I'm going to go ahead and apply a log base 5 of both sides. Okay, so in order for those to truly undo each other, we do need to make sure that their bases match. So the log base 5 of 5 to the x is equal to the log base 5 of 16. Okay, and again, the reason that we pick these to be the same is so that these would cancel out and just leave us with x. And so if we wanted to write our answer in its exact form, we would just simply say log base 5 of 16. And of course, if we are interested in getting the approximate form of that answer, we can go ahead and reach for the calculator here. So remember to plug this into the calculator. The sequence of buttons goes alpha, window, and then your number 5 key. And we just want to do a base 5 logarithm of 16. And when we press enter, we get this irrational number right here. So this is going to be a long decimal with no repeatable pattern that never ends in its digits. So we can round that to 3 decimal places by saying 1.723. Okay, so we get the 2 different versions of our answer just like this. Okay, so in order to go ahead and check, again, we were just going to go ahead and store that value into x and then type in our left-hand side and see if we press enter and get 30 for the right-hand side here. So I'm going to store that into x. And then I'm going to go ahead and type in my left-hand side. So 2 times 5 to the power of x minus 2. And if we get 30, then this is going to be a correct answer. And we do. Okay, so that is going to be a correct answer for us, so we can confirm that visually there. That's pretty good. You can see here that I did example 4 already here for you, just again because it would be so similar as the last example there, and also a little bit of a screenshot there to just confirm that we did get the right answer there. Again, I would encourage you to pause the video and work your way through those steps there to just make sure that this makes sense, because we have a base 3 on our exponential. That's why you see me applying a log base 3 of both sides to undo that exponential. All right, so now we're going to go ahead and move on to some equations that have logarithms in them, and you'll see here that the steps, again, are basically in the exact same spirit as all the other equations that we've solved this semester. We first want to isolate the log. Okay, now in terms of logs, what that's going to mean is that we may need to go ahead and combine multiple logs that we might have in the equation into a single log. So that would be using the properties that we discussed in the video before this one, 3.3. Okay, or Are we in 3.3? I teach so many lessons that I get my section numbers mixed around here. So that would not be 3.3 at all. I'm sorry. That would be 5.3. Okay, there we go. Sorry about that. So 5.3 video where we talked about the laws of logarithms. We may need to apply some of those logs to condense down, and then we undo it, of course, and we undo that by applying an exponential of both sides. So let's go ahead and see how that works here. Okay, so example 5, we have a couple of different logarithm equations here, and so again, the first step would always be to make sure that you isolate the log before you continue. Here in this example, that is already done for us, and so now we're just going to go ahead and think about undoing the log. Okay, now while there is a sense that we can perform an inverse operation to both sides of this equation, I think it's going to be a little bit easier if you think about it in terms of converting this equation from logarithm language to exponential language. And we can always do that, remember, by looping around, right? So if I go ahead and convert this to an exponential equation, I can do that by applying a base of 2 on my exponential, because that's the base of the log. So I'll say a base 2 there. And then I want to loop around to kind of figure out what the rest of the order of this equation would be, right? So that would be a base of 2 to the power of 3 is equal to the input, okay? So I'm going to say that. I'm going to say a base of 2 to the exponent of 3 is equal to our input, which is simply going to be 4x. And that's got a lot easier equation to solve because 2 to the third power, of course, is simply just 8. So we can see here pretty easily that the answer is simply going to be 2 here for us. Okay. Again, is one that you can go to the calculator and check if you like. Store 2 into x, and then type in the left-hand side and press enter and see if you get 3. Okay. Same thing on part B here. We need to do a little bit of work preliminarily to isolate that log because I have that 2 times in front. So I'm going to go ahead and divide by 2 on both sides first to start us off. And of course, that's going to leave us with the natural log of 3x on the left-hand side, and that is equal to the fraction 7 over 2. And of course, remember that the natural log, that is simply just a log with a base of e. So for purposes of being able to convert this to an exponential equation, remember we're going to start off with a base of e, and then we're going to loop around, right? So base of e to the power of 7 over 2 is equal to 3x. So e to the 7 over 2 is equal to 3x, and then we would just simply need to go ahead and divide both sides by 3 in order to get our final answer here. So if we were interested in the exact form of the answer, it would be just what I have written down there. It would be simply e to the power of 7 over 2, all divided by 3. But if we were interested in getting an approximation for this, which we are interested in here, let's go ahead and type that right into our calculator. So let's go ahead and clear all that out, and then I want to go ahead and do a fraction of e to the power of 7 over 2. All divided by 3. And in the calculator, it looks like that's going to give us 11.038 if we were to round to 3 decimal places. 11.038. Whatever representation we might be interested in there, exact or approximate, we are capable of doing both here, okay? So again, the general spirit of these problems is make sure that you isolate the log first and then undo the log by converting the equation to exponential language. Here in example 6, we have a logarithmic equation. This can't even talk. We have a log equation with more than one log in it. Okay, and so these are going to pop up from time to time, so it's important that we know how to deal with these. The idea is that we're going to go ahead and go to our last video, the 5.3 video, and we're going to reach for one of our properties of logs or laws of logarithms to take a look at that left-hand side and condense it down a little bit. Okay, so you can see here that we are doing the difference of the logs here, and so we have one of our properties that states that if I do the difference of the logs, that I can go ahead and condense that down into a single log by saying the natural log of the quotient of these two inputs. Okay, so my two inputs here are, of course, x and then your x plus 1. And so if I go ahead and write a quick quotient of those, then that would look like, of course, x divided by x plus 1. And I would just love to erase that and switch back to my pen. Please, OneNote, can I do that? Maybe? Okay, here we go. So x divided by x plus 1 is going to be our new input on a single log there that we condense down into. Okay, and now that we have condensed this down, we could go ahead and convert this into exponential language by remembering to loop around. So remember that the base here of this logarithm would be e, and we loop around and set it equal to the input here. So that would be e to the third power is going to be equal to x over x plus 1. Okay, now for the rest here, we're just going to need to think about how we're going to take this and isolate x in the problem, right? And that's going to be a problem because we have x not only in the numerator of the right-hand side, but also in the denominator. And so the first step of our work to try to get x isolated should be to get x out of the denominator. And we could do that simply by remembering that this is a divided by x plus 1. that I've got in my equation. And so if I go ahead and do the inverse operation of division, which of course is multiplication, I can go ahead and multiply the entire equation times x plus 1 and then get the following. I'm going to have Euler's number power times that expression, x plus 1. And then because I have it divided by x plus 1 and a times x plus 1, then on the right-hand side, these would just simply be inverse operations together, simply leaving us with x on the right-hand side. Okay, so we've gotten x out of the denominator, and now for the rest of the equation here, we're just going to need to try to do some operations to try to isolate x. And so to do that, I might go ahead and look at this e to the third as distributed inside. So I could say e to the third power times x plus e to the third times 1 is just e to the third, and that is equal to x. And then the goal here should be to try to get everything with an x in it onto one side and get everything else on the other side so that we can go ahead and try to factor out an x and then get it by itself. Okay, so for that reason, I'm going to go ahead and subtract away e to the third x from both sides. And so my equation now reads e to the third is equal to x minus e to the third times x. And because I have everything with an x in it on the right-hand side, I can go ahead and factor out an x from the right-hand side. So x times the expression 1 minus e to the third is going to be equal to e to the third on the left-hand side. One final step here, I'm just going to go ahead and divide both sides by that quantity that I'm multiplying times x. And in this case, that is going to be this quantity, 1 minus e to the third. And so we finally arrive at the exact form of my final answer. So that is going to be x is equal to e to the third divided by 1 minus e to the third. Again, if we were interested in the exact version of our final answer, then we would just go ahead and box this. But of course, if we were interested in the approximation, we can go ahead and type that into the calculator, which I will go ahead and do right now. So we're going to have e to the power of 3 divided by 1 minus e to the power of 3. And if we press enter on that, we can see here that that turns out to be a negative number. Negative 1.052 is what we're going to get as our approximation there. So let's go ahead and get that written down here. So negative 1.052. Okay, so you can see there that in an equation where you have more than one log, you're going to have to start yourself off by applying one of your logarithm laws from the last video. Again, that was 5.3. You condense it down into a single log, and then once you get this single log isolated and condensed down, you want to undo it by converting to exponent language, and then using your usual steps to try to isolate x in that problem. Number 7 has already been done for you just for the sake of the time in the video. You can see here that I'm now adding the logs in my original equation. So remember that we're going to reach for that product property from the previous video where if I do the sum of the logs, that's equal to the log of a product. So I'm going to multiply those two inputs there. And then you can see there the rest of how that's going to pan out, a little distributed property. And it basically turns into a quadratic. And I want to go ahead and talk about this here really quickly because you'll notice down here that I'm going to apply quadratic formula because that's not something that's going to factor because it involves Euler's number. And I haven't showed the work for quadratic formula here, again, just for sake of time in the video. We've talked a lot about quadratic formula in the past. But you end up with these two answers. And the reason that I want to go ahead and talk about this is because remember that when you check this, you're going to plug these answers back into your original equation. And you notice that one of our answers is a negative number, a negative 3.729. So if I scroll back up here to my original, notice that one of the things that I would have to plug back into, again, since you're plugging your number into x wherever you see it, you're going to have to take that negative number, which was negative 3.729, and plug it in for x in both of these places. What I want you to realize here is that you're going to be taking this negative number, and you're going to be plugging it into the log on that first one. Okay, so you're going to be doing that right here. And we just need to remember that you are never allowed to plug in a negative number into your log machine, okay? You may remember from our video where we talked about logs and their graph that the domain of your log function is specifically just those numbers from 0 to positive infinity. So basically, only your numbers that are strictly positive are allowed to be plugged into your natural log function, or really any log function. And so that is a quick way for me to confirm that I'm going to have an extraneous solution in this work here. Okay, so if I come back down here to my answers, again, because I would have to plug these answers back into my equation, and that would mean that I would be plugging back into a log, then I have to throw out this second answer that I got and only accept this first answer that I got to be true, because that is a positive number, and that is in the domain function. You can see over to the side, I did a quick screenshot of the calculator. Just go and confirm that that is going to be a correct answer here for us. And you'll notice that I went ahead and tested the version of this number that is not rounded. I wrote it down rounded on the page, but I'm testing it in the calculator without rounding, just so I confirm that that is the correct answer there. Okay. So as the last example here in this video, let's go ahead and take a look at example number 8, and then we'll be all finished up. Okay, so again, what we want to do is we want to notice here that we are doing a log base 10, and we have multiple log base 10s throughout our equation. So if you look at the right-hand side, what you'll notice is that I'm doing the difference of the logs. I've got the log base 10 minus the log base 10. And so what we can go ahead and do here is use one of our log properties to condense that down. And remember that if it's the difference of the logs, we can always condense that down into the single log of a quotient, okay? And so that would be the quotient of our two inputs here. So I'm going to go ahead and rewrite this as log with a base of 10. And also remember that log with a base of 10, that's your common log. And so for the rest of the problem here, I'm just going to go ahead and write it without the base written, because remember, if you see log without the base written, it's assumed to be a base of 10. Okay, so that's called your common log again. And so again, I can condense this down to the log of the quotient x minus 2 over x plus 2. And that's going to be important because when we set that equal to the common log of x minus 1 on the left-hand side, we can now go ahead and look at this as we have an equation with the same log on both sides, okay? We have the same log with the same base on both sides. So if you think about this for a second, really the only way that these two sides of the equation are going to be able to match up is if the inputs into these logs are the exact same. Again, that is because I'm taking the log with a base of 10 is equal to the log of the base of 10. And so again, the only way these are going to possibly match up for us is if these inputs are the exact same number. So at this point, instead of thinking about this as just applying an inverse operation to both sides, the way that I want you to think about this is just that. If you can get both sides to look like the log with the same base of something, then we could just go ahead and simply take these inputs and set them equal to each other, okay? So x minus 1 is going to be equal to the input on the right-hand side, which is this quotient, okay? And you can see here what that does is it takes our equation that was a logarithm equation, and now since we worked with it enough to the point where we can get to this point, now it's just one of those rational equations that we talked about a couple of lessons ago, okay? And the way that we want to go ahead and continue to do this is remember that we want to get x out of any denominator that we see, and so because I see a divided by x plus 2, I know that I can undo that by multiplying the entire equation times x plus 2. Okay, and so what that's going to do on the left-hand side is it's going to multiply times x minus 1. We're going to have x minus 1 times x plus 2 on the left. And then, of course, on the right-hand side, we look at those as inverse operations, right? If I have a divided by x plus 2 and a times x plus 2, those cancel each other out, just simply leaving us with the x minus 2 that was on top, okay? And now I have this converted to more of a quadratic equation, because if you FOIL out the left-hand side, you're going to end up with x squared plus x minus 2 is equal to x minus 2, and then we're just going to solve this like a quadratic equation by getting everything to one side and leaving 0 on the other side here. So if I subtract x from both sides and then add 2 to both sides, I'm going to end up with the following. I'm going to end up with here x squared plus 0 effectively, okay? So I'm going to have actually x squared, okay, is equal to 0. In which case, if you were to take a plus or minus square root of both sides, you would find here that playing the role of x is simply just going to be 0. And it looks like OneNote just crashed there for me, so let me go ahead and reopen that. And we'll get our final result written down. Okay, so x squared is equal to 0. So again, if we were to go ahead and apply a plus or minus square root of both sides, we would find here that our final result is x is equal to 0. Okay, and so let's go ahead and check that really quickly in the calculator. All right, so if I go back to the calculator and I store our result into x, so 0 stored into x, press enter. We have that stored in there, and now we're going to go ahead and type in the left-hand side and then separately type in the right-hand side and see that they end up being the same number here. So on the left-hand side of my equation, I had the common log of x minus 1. So the common log of x minus 1 is equal to this right here. Interesting. So check out what happened, right? I have this number we ended up with a complex number, and when you guys solve these equations, we're only interested in getting real number results, and so what that's going to mean is that we're going to have to take our answer and throw it out. It's an extraneous solution, okay? When we try to check this result, it creates a non-real result on the left-hand side of our equation, so we're going to go ahead and call that extraneous, which means that the only solution that we ended up getting is actually going to have to be thrown out. So our proper conclusion here would be that we have no solution to this equation, okay? So that is going to have to be something that you're on the lookout for when you solve certain logarithm equations like this. So that's going to do it for this video. Thank you very much for your attention. If you guys have any questions whatsoever, as always, then feel free to let me know. But yeah, we always isolate and then we undo to solve these equations. So I hope this video has been helpful to you. Thank you very much for watching, and I'll speak with you in the next one.